Hey, have you ever felt like you need some kind of secret decoder ring just to figure out what's written on your electronics? Well, today we're going to crack that code. We're talking volts, amps, watts, the whole shebang. And trust me, by the end of this, you are going to be fluent in the language of electricity.
I mean, it all starts with something simple, right? Like the tiny print on your phone charger. You see those letters? V, A, W? And you probably just think, technical specs. But they're not. They actually tell a story. So, what is the story behind these kind of cryptic symbols? Well, it's a tale of pressure, flow, and power. Let's dive in and start at the beginning.
Okay, so first up is voltage. Now, I want you to think of it like the starting pistol in a race. It's all about the potential. It's that coiled up energy that's just waiting, just begging to be unleashed. It is the readiness for action. So what exactly is voltage then? Okay, let's use an analogy. Imagine a giant water tower. The higher up that water is, the more immense the pressure builds up at the pipe way down at the bottom, right? That is voltage. It's the electrical pressure in a circuit. It's this force that's just ready and waiting to push everything forward. So we measure this electrical pressure in volts, and you'll always see it represented by a capital V. Simple enough. It is the fundamental force, the thing that gets everything moving in the first place. So what happens when we open the floodgates? Well, with pressure, you get flow. But it's not always a smooth ride. This is where we meet two new characters in our electrical story. You've got current, who's like the hero trying to get through, and then you have resistance, the villain trying to stop it. So if voltage is the push, then current is the actual river of electricity that starts flowing because of that push. It's the electrons physically on the move, zipping through the wire, carrying energy and doing all the actual work. This is the action part of our story. And we measure this flow in amps. That's just short for amperes. But here's a fun little quirk for you. The symbol for the quantity of current is actually the letter I. A little weird, I know. So when you see amps or A on your charger, it's telling you exactly how much of that electrical juice is actually flowing through.
But, of course, nothing flows without a little friction, right? And that's where resistance comes into play. Just think about a really narrow pipe trying to carry a lot of water. It's going to slow it down. That's what resistance does in a wire. It slows down the flow of those electrons. It's basically the brakes in the system, and it gives us control.
Now, resistance is measured in something called ohms, and it has this really cool symbol, the Greek letter omega. The thing to remember here, the crucial point, is that every material, from the big wires in your walls to the teeny tiny filament in a light bulb, puts up at least some kind of fight against the current. So you can really see this constant battle playing out. You've got current, measured in amps, trying to surge forward, and then you've got resistance, measured in ohms, pushing back. It is this eternal tug of war that makes, well, everything in our electrical world work the way it does. All right, now just for a little extra credit here, there's actually a flip side to resistance. It's a property called conductance, and it's all about how easy it is for current to flow. So if resistance is the friction, then conductance is the smooth sailing. They're really just two sides of the same electrical coin. Okay, so we've got pressure, flow, friction. But so what? Why does any of this matter? Well, this is where it gets really exciting. This is the whole reason we care about any of this. It's how we actually do things. Light up our homes, charge our phones, power our entire lives. And that brings us to the grand finale, power and energy. So, power, it's all about speed. Think of it like a sprinter. It's not about how far the sprinter runs, it's about how fast they run it. And a powerful device is just like an electrical sprinter. It uses a whole lot of energy in a very short burst. And this, my friends, brings us full circle, right back to that third and final piece of the puzzle on your charger. Power is measured in watts, symbolized by a capital W. So that 100-watt light bulb, it isn't just bright. That number is telling you exactly how fast it's chugging down electricity. And now for the secret that ties this whole thing together. See, power isn't some magical, separate concept. Nope, it is the direct result of the pressure and the flow we've already been talking about. Watts are simply volts multiplied by amps. That's it. The more push and the more flow, the more power you get. It's really that simple. People mix up power and energy all the time, but here is the dead simple way to remember it. Power is your speed. Energy is the total distance you've traveled. Think about it. A fast car has a ton of power, but the energy it actually uses,
Well, that depends on how long you actually drive it for. And that total distance traveled, that's measured in kilowatt hours, or kWh. Now, why should you care about this one? Because that's what's on your bill. That's what you're paying for. Your electricity company, they don't care how fast your car is. They care how far you drove it. You get billed for the total energy you consume, not the raw power of your gadgets. All right, we've met all the players in our story. We know who's who. So now let's bring them all together for the final reveal. This is your master key, your Rosetta Stone for unlocking the language of electricity. And here it is, your electrical cheat sheet. Let's run it down. Voltage, that's the push, the potential. Current, that's the flow. Resistance, that's the friction holding it back. Power, that's the rate you're using energy. And energy itself, that's the total capacity to do work. This right here is everything you need to know, all in one place. So look, if you walk away with just one single thing today, let it be this. The pressure from the volts times the flow from the amps equals the work rate in watts. That simple, elegant little equation is what powers our entire modern world. So I want you to go on a little scavenger hunt. Look at the devices around you right now. Your TV, your microwave, that laptop charger again. Now that you speak the language, now that you can read the code, which one of them suddenly makes a whole lot more sense? Pretty cool, right? Now go out and decode your world.